To illustrate application of the Kirchhoff current law and Kirchhoff voltage law, we're going to look at the following example. We have a couple of values which are given for voltage and currents, and some of them indicated in red are the ones which we have to find. Using Kirchhoff current law and Kirchhoff voltage law, we will try to answer that question. So don't forget two things. Kirchhoff current law always applies at a node, and it basically says that the algebraic sum of all the currents that are entering the node equals the algebraic sum of all the currents that are leaving the node. Kirchhoff voltage law, on the other side, applies only at a loop. It indicates that the algebraic sum of all the voltages inside the loop equals to 0, and one very important point in here, never ever change the direction of the loop. Once you choose one particular direction for one of the loops, exactly the same direction has to be applied for every other loop. So in our question, we will have to find currents I2 and I4. Let's start with them. This requires application of the Kirchhoff current law, which is something that forces us to pick up to a particular note. So I have indication in here of note A and note B, and all I'm going to do is apply Kirchhoff current law for each one of them. So Kirchhoff current law for note A is telling me that the sum of all the currents entering the notes, which are I2 and the 6 amp currents, equals to the sum of all the currents which are leaving the node, which in this case is the 2 amps. From here, we can calculate the value of I2, which is negative 4 amps. One quick note in here, the fact that we end up on a negative current, negative value, just indicates that the originally given direction of the current IT was wrong. In reality, the current flows in opposite direction. Now let's do Kirchhoff's current law at node B. Applying the same, we have algebraic sum of currents entering the node, which is only one current at 3 amp, should equal the algebraic sum of all the currents leaving the node, which are the currents 6 amp and I4. From here, we can calculate the value of current I4, which is going to come up at negative 3 amp. So again, exactly the same logic applies in here. The direction of current I4, so the same rule applies in here. The direction of current I4, originally given on the diagram indicated on the diagram, is not being correctly chosen. In reality, current I4 goes into the opposite direction of the one indicated on the diagram. Now let's move to the voltages. Once we're talking voltages, we need to concentrate on Kirchhoff voltage law, which means we have to choose the loops. As already mentioned, once a direction for a loop is being chosen, do not change that direction. It has to be exactly the same for every single loop in the diagram. So let's start in here with Kirchhoff voltage law, one step at a time. So Kirchhoff voltage law being applied at loop number 1 indicates that the sum of all the voltages inside the loop is going to be 0. So it basically tells me that if I take the voltage across element A, 6 volt, and I add to it voltage V2, the result is going to be 0. So from here, a voltage V2 comes at 6 volt. Now we will do current voltage law for the second loop. Loop number 2 gives me a negative V2 plus V3 and negative 2 volts. All of this should be 0, which ends up on an equation V3 equals V2 plus 2. I will keep it on mind and try to work with whatever I have found. Because the value for V2 is known as negative 6, we could say that V3 is negative 6 plus 2, eventually ending up on negative 4 volts. So we're ready with the value of V3. Moving to the third loop. So Kirchhoff voltage law at loop no 3. Following the direction at loop number 3, we could write that the negative 2 volts and the negative 4 plus V6 should give me 0. So from here, V6 equals 2 volts.